I do have work to do. I do have work that needs to be completed. I do have things that need to be done, but I'll be honest, I can't. I need a break. I'm bored. I'm just bored out of my mind. I spent the day-to-day working on the website as much as I could, working on the video as much as I could, and in fact, I'm rendering the animation for the video right now, in the background. This right here, hi there, Black Thunder, welcome back. This right here is the animation for the video, it's happening, but I am just bored out of my mind, so I need to do something interesting. I need to do something to not go crazy, not go mental. And so that's precisely why we're gonna be doing science. Also, congratulations on the new boots.
$300 boots, but I've had the old ones for a decade, so pretty good ROI.
Good for you. Right.
Is that the Death Note?
Close. Is the drunk science notebook. You can't really see it, or can you actually? Oh, I think you might. Is the camera not in focus? I think it might not be. Hold on.
Yeah, it's good.
Oh, there we go. Now it's more in focus.
Just a black notebook with white-ish text on it, so it's kind of the same.
Right, but that will be important later. Actually, now that I think about it, I don't want to be writing into it instantly. First, we need to do some research. Do we not? A break, you say? Yeah, a break. I need to go to church and say, "Forgive me, Father, if I have sinned" or something. I haven't watched one of the videos months. Months!
No, he's signed.
I need to go to church. I mean, listen, I sometimes forget that people go to church and say, "Forgive me, Father, for I have sinned." Usually they say that to me. Right, so today we'll be dealing with physics. I'm a simple man, alright? It's a long day at work. I come back home. Someone's calling me daddy. That helps, you know? I won't deny this. Who am I to deny it? I won't be lying. Anyway, our unholy fingerbowl. I would avert your eyes if I were you, because I'm going to be learning something that you know, I imagine, very well. And that is, I can actually note it down and you will instantly know. I can note down the first part out of the 4 and you will know exactly what it will be. I can note down the first character of the first part, I imagine you will already know what it will be. There we go.
The alphabet.
Close. Really close.
Oh, okay.
Just
we're doing alchemy, huh?
So an inverted triangle alphabet. Close. Not that far off, I suppose.
Water.
It is actually... It's... Oh, that's actually... Well, no, I went overboard with it, but that would be a nice... I think row, right? I think row. Vectors, in a way, in a kind of way. Vectors of calculus. But yeah, there's just... I'm bored out of my mind. I want to just learn something because, as I mentioned, I'll go crazy if I want. And so I've picked a topic out of my randomness of topics. Yes, exactly. That's exactly right now, Holy Fingerbowl. It is Maxwell. It is obviously Maxwell's equations. But we'll need to... I noted down this one simply because I knew that you could tell really easily. But that's not where we'll start. We won't start the Maxwell's equation. We'll start with the nabla. Is that what it's called? I always am uncertain of that character. Where is it? The del operator. Yes. The del operator, which... Oh, jeez. Lemon will have a field day. Used to be Nabla, now it's called the del operator. No, if I'm not mistaken, the character is called Nabla, the operator is called del. Or was it really used to be Nabla and is now del? I always thought that the character was del. Right, so basically when we have a del f is just, oh, that looks actually relatively tame, I would say, because it's defined as, I'm going to rewrite it for myself simply because it's going to make this easier for me, believe it or not, of this, all of this of f, and that is e xi subscript to a subscript, because physics, and then in relation to, now that is partial xi. Okay, so this is your nabla, del, sorry. Mickey, one of my teammates in FTC is copying, and he grinded CAD for 8 hours straight, slept for 3 hours, then 5 hours of CAD, and then 2 more hours of engineering and other robotics related stuff. Wait, what is FTC? Federal Trading Commission? What was FTC? I don't think that's the one.
Faster than light?
Fourier transform covariant? What are we dealing with? I need a drink. Alright. First tech competition, I see. Okay.
I think it's the third, actually.
I would know. How would I know? First tech challenge, I see, okay. Is copying you. Oh, copying me because I can't believe it. I haven't done CAD in such a long time. If I'm not mistaken, this is actually the last thing I did with CAD, and I have never even gotten to fully assemble it. Don't worry. One day I'm gonna get back to you. Anyway, this is actually pretty straightforward now I think about it. I mean, this is just gradient. It's a sum of all of, wait, but these are not evaluated derivatives, are they? So basically what it would give you is, it would give you a vector, correct? Unless the E isn't the same one as in mathematics, it usually is. Oh, you are not fun. Oh, no. No, you are not fun. Okay. I mean, okay, that might be fun, but I don't, that's going to have ramifications. That's because this is del on a function, but at the same time, you can have a del on a multivariable function, in which scenario, it's noted down on Wikipedia with a capital F, which, I mean, just terrible notation. Fine, fuck it, capital F. In which case you can have a dot product or a cross product with it. Oh, I hate that. But I suppose, no, it doesn't make sense. Because then they are, respectively, just sums, like so, with, on the inside, EXI, like so. And then, once again, it's partial. Yeah, once again, it's just partial derivative to the appropriate xi. The only difference is that then it's a dot f versus a cross f. That I find a bit confusing because in order for this to work, nice hair, be careful with the cam. Cheers. Cheers actually for a warning, but I imagine I will be always looking down, hopefully, so I'm hoping that will save me.
I think they meant bumping it, but
Oh
two.
no, it is actually surprisingly far away. You wouldn't think it. Hold on. Do I have anything for scale? I don't think I do.
I see a butterfly knife.
Well, this one. Hold on. Too small. But was I saying? Oh yeah, right. In order for this to make sense in my head, I would need the E to be a vector, and that doesn't make sense. That doesn't sit right with me. Because usually, as far as I'm aware, E noted down like this refers to a basis. Which... Oh, but basis can still be expressed. No, that's awful. Okay. Be careful. Be careful. I mean, no, I'm not gonna bump the camera. Don't worry, it's far away.
I think they're talking about the knife.
Yeah, the knife. I'm also fine with the knife. Give me a second. Let me show you actually how much space there is between the camera and the table. Hold on.
Hi.
See? There's lots. Hi, the macaroni. How you doing? I think what happens in this scenario is... Imagine he slits his finger because he misses the Baleson trick. It's a common rule that you need to get used to. My knives don't cut me. They can't. They're unable to.
Yeah. You only ever grab one handle.
Yeah, I mean, exactly. No.
Unless you're an idiot like me, and then you do cut your finger. And then you learn the rule very quick.
Yeah, you have to remember to never grab a knife by its blade, because if you grab it by its blade, that's really dangerous.
Absolutely.
Yeah. Do a rollover.
Indubitably.
Hi, Ash, by the way.
Hi, Ash.
Hello.
Ash, I have a question. When you have an...
Do go.
because I'm looking into the del operator almost for the Maxwell's equations. And I hit basically the E of the some kind of coordinate, right? And how should I explain this? Can you see these two equations at the bottom clearly, or can you not see them clearly?
Yeah, one's a dot product, one's a cross product.
Yeah, the pickle I have is that in order for this to make sense, f has to be a vector, which makes sense. That's reasonable. It's defined as a vector, that's fine. But also,
Yeah.
the partial on this side has to be a vector. And the partial cannot be a vector. What has to be a vector has to be the e. But as far as I'm aware, e noted down like this, that would be the basis, right?
I suppose.
Because that's the only way I can make sense of it. So, you know, ex would be just
I
the
see what
basis
you're
that
saying,
creates the
yes.
x.
I see what you're saying.
Yeah, that's the only way I can think of it. Make it. I saw my friend play around these things and bleed out. My knives don't cut me. Don't worry. That's it. That's just how it works. Yeah, well, except I suppose Mike could be the only exception, but Mike is Mike.
Who's Mike?
My big knife.
Oh, gotcha.
Yes.
Like machete big or steak knife big?
a steak knife is big,
Oh, okay.
but Mike
Oh.
Mike is dangerous.
I played with Mike.
You did play with Mike, yeah. And I honestly, it did for a significant amount of time. Just felt like, it was terrifying to see Ash play with Mike, because Mike is genuinely the one knife that I need to be careful around.
You should show us Mike.
Hold on.
And I was cutting a corny bar open with it.
Yeah, hold on. Let me get Mike. Oh, one of his googly eyes fell out. Damn it.
No.
How will he see what he's cutting?
Everyone said hi to Mike. This is Mike.
Hello, Mike.
This is the one knife I have that's actually sharp, and yeah.
Yeah.
This one is dangerous.
Well, that's bigger than steak knife.
I don't know how big steak knives are.
Well, a machete is like almost a sword, which is why I was asking.
Yeah, which is that's I know how big a machete is. That's why I didn't say machete.
Yeah. Yeah.
Okay, then this makes sense because this is, by the way, we're only 15 minutes in, and this is already a very make it kind of live stream.
Learning physics and playing with knives.
Exactly. All right. Then I can make sense of all of these. Conceptually, that makes sense. It also makes sense as a gradient, I would say. As a gradient, it also makes sense. Well, this one is trivial to understand why this would be a gradient. Because that's basically like you have a multidimensional function, you see where it goes effectively. That's simple. What's more tricky for me is to have a good concept of the dot product and cross product of the del. And even better, oh, you are joking. Even better, the cross product has ramifications. Oh, why does it always need to have ramifications? Because the dot product,
Ramifications in what sense?
it can
Ramifications.
be written out differently. It can be written out, and I feel like I will need to. Now, if I assume x to be the first, second, third, see xy. What is the symbol for modulo? Can I just use a percentage? Or is there, I imagine there's another symbol for modulo that's more accurate, more apt to mathematics. So if I want to,
What do you mean modulo?
well, when I want to do like
I think
a
it's
remainder,
mod parentheses.
remainder of division by 3, for example, how do I do that?
Oh, just write like smaller case r and then the number after it. Doesn't matter.
So sort of like R3 of x,
Yeah.
like this.
Wait, hold on. Your stream is a bit behind.
Bit.
No. Maybe like 5 is equal to 1r2 is what I meant.
But I need to note down, you know what, I'm just gonna do the mod because that was gonna be easier.
Yeah,
That's because if I do the mod, then I can note it down a bit in a bit more of a simple manner, which is like this, like this, like this, like this, and then it's a partial f partial f of, I'm gonna run out of space because this is also f. This is e of mod 3 of I, like this. That's the coordinate. Then this one is, oh wait, well, that's of x, right? Then this one will be x mod 3 of I, but then plus 2.
Oh, you're just trying to write it in summation notation.
Yeah, exactly. That's because I'm trying to make sense of it, and I think that is gonna help me.
We have an operator for this. Wait, let me try and remember it. It's like the bigger brother of the Dirac delta. Hold on.
Well, and then the x is just, oh no, because that's z to y, y to z, so they just flip. Oh, that's tedious.
Summation notation sounds like a very underground Midwest emo band.
All right.
How did I forget what it's called? God damn it.
I need to play some music for myself for this.
It had an iconic name too, is the problem. Levi-Civita, yeah.
Might be language barrier, but isn't mergeable language with congruence? Basically, for example, arg z is equivalent to 0 to pi. I don't remember which one was arg. System del and surgical. Okay, so del on its own is basically a gradient. The dot product, cross product are a bit more tricky. Okay, but no, the dot product looks equivalent, question mark. I think dot product is equivalent to just applying on the function.
Yeah, Levi-Civita, yeah, exactly. Sorry, did he say something? I was reading, yeah.
I'm wondering if this is these two, are they equivalent? Because right here you're multiplying the basis by the partial in relation to a special coordinate. Right here. No, the gonash.
No, I was just going to say that when you're taking the gradient of a function, you get a vector back. But when you're taking the dot product in the way that you annotated there, you're actually getting a scalar at the end. They're definitely not the same thing.
Yes. Yes. Dot product is a magnitude. That's what it looks like. Because it's just the three partials summed together. Like this genuinely equals out to a sum of just partial of fxi to just xi. So this genuinely does look like just the magnitude of the gradient. Or at least, yes, magnitude of the gradient, right.
I mean, yeah, sure.
Yeah,
Kind
sure.
of.
What do you mean kind of? This is maths. What do you mean kind of?
I don't know. I don't know about the physical interpretation of it, but you know, mathematically, yes, it's just a scalar sum, nothing more. Like whenever I
This isn't a physical
hesitate-
interpretation. We're not doing physics yet.
Oh, okay, then perfect. Yes.
Like, I'm just getting used to the del. We haven't gotten to the maximals. Okay. Cross is going to be a problem.
For cross, I have a very vague sort of intuition for this.
I think I might develop one for myself in a second because I think I see something, but I'm not certain. Because what it is it's obviously vector. Wait, vector? Yeah, it's a vector.
Yeah.
Okay, good. It's a vector, so we multiply each one by. Well, we do it in 3 dimensions. So for now, let's just do ex. It's just a sum of 3 of them, so it doesn't really matter. So we can only handle 1 and think about 1 like direction. So we have fz in relation to y and fy in relation to z. That's what we have. Now, there feels... Okay. Let's imagine there's a planar function. This is basically derivative... Oh, curious. Okay, so it's basically how... Oh no, hold on. Because that function is... It's R3 to R3. It has to be. Right. Oh, I'm an idiot.
Is it R3 to R3? Hold on.
It has to be R3 to R3 because otherwise how are you going to take a cross between the del and f? The capital F is the function of R3 to R3. Because otherwise you wouldn't be able to do this.
Oh yeah, I see what you mean. Yeah, yeah.
So this part, how much the function is changing in the z output in relation to the y output, y input. How
Yeah,
much?
you're essentially really close to how I think of it.
Yeah. It eludes me because there's a lot there. It's 6-dimensional. That's pretty rough. I'm trying to imagine a 6-dimensional graph. Give me a second. Right. Right. Yes. I'm about to run out, by the way. the cross product produces a new vector that is perpendicular to the original vector. That's why I remember it being taught. Haven't looked more into it. No. Cross, that's simple. I'm trying to understand the del cross a function. That's what I'm trying to understand. Also, actually, wait, would this happen in Maxwell's equations? Does this happen in Maxwell's equations? Is this
Yes, I
an
think one of
R3? Are fields R3 to R3? I mean, obviously they are R3 like the first one, that's obvious, but are they 2 R3 as well?
That's what I was a bit confused about, but
Because
I don't think they have to be.
well, I mean, they definitely don't have to be, but you know, is the electric field R3 to R3?
I think it might just be R3 to R.
That's
Don't
what.
quote me on that.
Well, that's my intuition as well. That would be my intuition as well. But you know, intuition is worthless, so let me just look into it. No, it has direction. It is R3 to R3. I'll be damned.
Oh my god, yeah. Yeah, never mind, yeah.
It is R3 to R3. I'll be damned. Okay. So,
Alright, because it's a vector field, not a scalar field, bruh. Okay, yeah.
it still doesn't make much sense in my head, but I'll just accept it as a fact.
Honestly, I hate electromagnetism.
Well, I've never really gotten that deep into it.
The problem is, at one point in life, I tried to connect electromagnetism with differential geometry. I failed, and then I hated electromagnetism.
So is it true that at some point you just start hating on it, on the field of science you're the most into,
That you're the most into? No.
or that you know about the most?
It usually that only happens if you're doing theoretical stuff. And then
Right.
you don't hate it on the field of science you're into, only like everything surrounding it. The closer the worse.
Gotcha.
The dot is simple because then, like, you know, del D to rho V, where that is electric charge density, that makes sense because that basically gives you the magnitude of the slope is just the electric charge density. That's simple. Then the del of B is equal, del dot B equal to 0, also simple. Right? Because that basically means that the magnitude slope has to be null, which, how does that square with monopoles actually?
Sorry?
Can, when it comes to Maxwell's equations, the del B, del
Yes.
dot B equals 0, how does this square with monopoles?
Del of B equals 0.
Del dot
Could you-
B equals 0, yeah.
Oh, it's del dot B equals 0.
Yes.
How is B defined again? Is
That's the magnetic field, if I recall correctly.
del dot B is defined as
Wait, is
0. That means that
Let me check.
there is no divergence
Magnetic-
in the magnetic field. And
Magnetic
what that
flux.
means,
This is because
Yeah.
magnetic monopoles can't exist. Well, don't be so closed-minded now.
no. It's not because magnetic poles can exist. You actually have it reversed. This is the reason why magnetic poles can't exist. It's not 0 because they can't exist. They can't exist because it's 0. But you know, topological constraints aside and whatever. But del dot B equals 0 essentially means that
The magnitude of the gradient is not at any point. Or the magnitude of the gradient is just not, which, yeah.
I mean, kinda, but a more simpler way to think about it, the way physicists usually approach it, is that you're just saying that the divergence of the magnetic field is zero. That means if you take any volume in R3, then the number of magnetic lines going inside are the same as the number of magnetic fields going outside, if I recall correctly.
Or like if you have a circle, then if you imagine just arrows on the circle, the net direction of these arrows will be zero.
Yeah, I think that's the Stokes theorem for the surfaced one, I think.
Is that really one of the Stokes theorems?
Yeah, the 2D one. I forgot what it's
Purely
called.
on accident. I have no idea what any of the Stokes theorems are. That is hilarious.
I mean, the entire thing about Stokes theorem is just look at what's happening inside a volume and then relate it to what you're seeing on the surface of the volume. Then it also makes sense to say that the divergence on the south and north pole cancel each other out and sum to zero. I mean,
I wasn't certain, that's why
yeah.
I just said across the entire thing.
I mean, I guess so. I mean, if you were to like isolate Earth completely and then enclose it in some container, then you would say that that container has no divergence, if that's what you mean. But, since we're so small compared to the magnetic field, we do actually see magnetic effects of the North and South Pole.
I should specify, Ash,
Yes?
that Unholy Thinkable is actually extremely knowledgeable about this topic.
That's good.
Yeah. I would say it's actually convenient they're here. Because I imagine there are many people who I would know who would potentially know more about Maxwell's. Because Maxwell's is tricky, isn't it? It's not really... I don't know that many theoretical physicists who are into Maxwell's equations.
I'll do Maxwell's equation next semester, probably. Because I'm gonna do a lot of things with fields and stuff, so Maxwell's equations are just gonna get grinded in between for no reason.
Curl operator. The measure of rotation of the vector field.
Essentially, yes. Though I never quite understood this, I'm gonna be fairly honest, curl is something that I never, ever got. To this day. I'd be more than happy if someone's willing to offer me an explanation.
There's this banger website, by the way, which I am learning from. It's
Is it
called...
brilliant.org?
No, it's called maxwells-equations.com.
Wow.
I don't know, just seemed like a good source for the topic.
Back in my day, piracy sites still had creative names.
Skidrow.org.
Oh, and this is apparently called the divergence operator.
Yeah, that's what I was talking about, divergence of the magnetic field, yes.
Okay, but
Divergence
then that
is
makes
easy.
sense. So, that makes a lot of sense, both of them. That's good. Do I have anything on me? Well, yeah, I'm running out of space. Oh, whatever, as if that matters. This is not the one I used in the video, by the way. It's close. Okay, then the equations. Let us note them down. Oh, you know what? Let's note them down. Let's add a bit more gravitas to the situation. I get mixed up because I haven't really delved much into the mathematical meaning behind these equations. Yeah, which is precisely why you're the person who would be most knowledgeable in them. Because no one ever delves into Maxwell's equations for the deep mathematical meaning. I've genuinely never seen anyone who has interest in theoretical physics go into Maxwell's equations. It's always people who are into engineering. Don't mind that, by the way,
That's
that's
actually such a fair point to make.
Yeah. Delta, jeez, del. They removed the ta. Is equal to rho v. Then del 0. del cross E and del cross H, and they are minus partial B in relation to time and partial dt plus j.
For some reason, Unholy Thible's like comments aren't visible in top chat. I don't know why.
Unholy. Are you going to note down the integral and differential form of these equations? For now, just the equations on their own, because for now I want to get a good feel for what they are as on their face value. I like this website so much. They are basically, the website there is basically what we're trying to do for quantum mechanics.
Delta dot D, delta dot B. What is D?
Magnetic flux, I think. Electric flux.
Ah.
Sorry, electric flux density, obviously, yeah. Magnetic is B.
What is electric flux density, boys?
It's quite descriptive of a name. Do you know flux?
I only know it from the physics point of view, which is the number
Yes.
of lines passing through a unit area.
Yes. I mean, I don't think there is a. I don't know if there is a. I've never had a like maths point of view on flux. I've only seen it
Yeah,
used in
me neither.
physics. More specifically, I've only exclusively seen it used in electricity as well, despite it not being an electrical concept. I've
I'm
only
pretty
seen
sure
it.
it has something to do more with fluids than anything.
Never seen it used in fluids.
No, I have seen it used in fluids. That's why I'm.
I
But
haven't.
anyway, it doesn't
I
matter.
remember the one place actually where I have seen it used outside of electricity, and that was as an example on physics stack exchange when I was researching the electricity video a couple of years back. Because then someone used not electricity as an analogy and they for flux. They were explaining flux.
Okay, so delta B has to be 0. That makes
Who
sense.
has made that website? That's incredible.
The curl of the electric field is the derivative of the magnetic field with respect to what?
Yeah, this respect to time.
With respect to time. Okay, let me think about this. Because if you think about the curl not being 0, then that means that if you integrate like around an infinitesimal loop once, your field is not conservative. So the curl not being 0 is a measure of how non-conservative your field is. And then how non-conservative your field is how much the magnetic field is changing essentially.
Wait, does this mean that if you have a constant magnetic field, the constant divergence of the flux of magnetic field, then the electric field won't be curling?
Sorry?
Because this is the magnetic flux in relation to time. Oh, but this flux, that throws for a loop. I need a refresher on the flux in order to, if I'm trying to have a good flux, if I'm trying to have a good understanding, I can't just go off what I know. Okay. So yeah, flux is I per. I'm just kidding, Olivia. There we go. Flux as a scalar is defined. I have a whole bunch of. Hold on, I have a whole bunch of solder stuck to the table. It's making it really hard to write.
Sorry, laptop died for a second.
I'm out. How am I supposed to do physics now?
All right, so yes. So essentially, B is magnetic flux or magnetic field or
B is flux.
What is the difference between a flux and a
The camera died. The flux, well, think of flux, it's quite descriptive. Think of field as just how much of something there is. Think of flux as how much of something is passing through, right? Hold on. It's actually exactly why I'm refreshing myself on the concept of flux in general.
That's such horrible notation. I don't know. Maybe I'm just the one who's being iffy about it, but
I mean, it's pretty rough field, pun intended, I suppose. You're welcome. Okay, so I is just limit as delta t approaches 0. Why did they feel the need to define derivative this way of delta q, delta t? That's such a, because this is genuinely what's written in Wikipedia. That's, am I crazy here? This is just like a really silly way to note down the derivative. I think Gibbs unified theorem uses flux outside of electrodynamics. Is that fluid dynamics? Alright, I'm going on another tangent. Yeah, Gibbs theorem. Statistical mechanics. Yeah, and this trajectories, that makes sense. That would make sense. Right, hold on. Yeah, so this is just, well, this is just amperage. I couldn't help but notice this is just charge per time. That's just amperage. Amperage per area. I mean, okay, Q for quantity, so I suppose the more generalized isn't amperage, but you know, I'm obviously going in the direction of electricity, so.
we've lost a soldier.
I like that because I'm in streamer mode, I couldn't actually hear Macaroni leave, but I heard it in the, like, from your Discord.
Oh yeah, you can hear my Discord time to time. J is the current density.
Is it? Because it's noted, this is what I've seen as definition of flux as a single scalar.
What is current density? What are these concepts, man? Is it just charge per unit volume?
No, it's per area.
Oh. Why area? What?
And it's not
What?
charge, it's amperage. So it's a measure, you have some kind of amount of charge, you have an area, and you have it pass through the area, right? You have, if you have more charge, it increases. If it passes quicker, it increases. And through a smaller area, it increases.
Okay, I get it. You know, I vaguely remember there being like some formula, I is equal to NAQV, at some point in high school.
I is equal what?
NAQV. N is the number of particles or like electrons.
Capital A?
Yeah, capital A is area. Q
QV.
was the,
And that was for I.
yeah.
Because I would be amperage, I'm guessing.
No, I is current. Yeah, amperage. Yeah, current. Yeah.
Wait, hold on, hold on, you threw me for a loop. This is N,
Yeah, number of electrons.
this is M, N, V, Q, all of that per time. That's basically what it would be. Which, the problem here is that the N and V don't know what they're doing there.
Honestly, I have no idea either. I just did this in high school, unfortunately. I don't have much insight to give on this.
Alright. So the electric flux density, also it's electric flux density, and it is
There's flux density as well.
D is equal to epsilon E, where this is the permittivity, and this is the electric field? Huh? Yes.
What is that? Ah. So, given an electric field, you just multiply it by permittivity, and then you get the flux density.
It would appear so, and it would appear that you can repeat the process for the magnetic. H, I don't remember what was the constant.
I mean,
Okay.
somehow this kind of makes sense, I think.
Well, the problem.
Yeah, it's permeability for, yeah.
Hold on. So it's epsilon. You said it kind of makes sense. That's tricky for me because can you not rewrite, because if mu is a constant, right?
Yeah?
Then can you not rewrite the equation as del cross E, the curl of the electric field on its own, just electric, is equal to minus partial of mu magnetic by in relation to time.
I mean, it's not that simple because, mu and epsilon are constants, yes, but they also depend on, for example, what medium you're working in. Like these are for vacuum, like epsilon and mu, the ones you're probably seeing right now are the
Oh, you
values
know
for
what? No, that
vacuum.
makes sense. That actually makes sense. So, like, if the permittivity is constant across something, yeah, no, that makes sense. Let me actually
Yeah.
look into it because I can just permittivity of fundamental magical parameters, which is reciprocation, and divided by some epsilon.
There was some weird ass formula for permittivity as well that we went over in high school when we were doing like capacitors or something, but again, I don't remember much of it.
Does the permittivity
This is ancient knowledge to me, which is crazy because I'm not that far into education for knowledge to be ancient.
There's one thing that messes with me, an unholy thing about. Would you mind if I ask you about it? Because conceptually, that's something I don't quite understand. Why does the electric field have direction? I don't understand. Does it actually have direction? No, it has to, because otherwise you can't cross. It needs to have a direction.
I mean, it was R3 to R3 as we established, so.
Yeah, I mean, it has to. That's what I'm saying, because the reason why I said that it has to be R3 to R3 is because otherwise you wouldn't be able to take the cross.
Yeah, I suppose. Why does it have a direction?
It must. If it doesn't have direction, you cannot take the cross.
I mean, I guess one way to think of it is that the electric field would describe how a test particle would move if there was just the electric field there.
No.
No, it doesn't.
No, because then you would. Because then I'm sorry, but that would be idiotic.
Isn't that the entire point of the electric field, though?
No, because then what you would do. Wait, if you had. No. Think about it this way.
Yeah.
What if you had the electric field that just describes the magnitude, no direction, right?
Yeah.
Then you take del of the electric field, of that new electric field, which I'm gonna just note down with a bar on top, because why not? You take
Yeah.
del of that electric field. What do you get then?
Del of that electric field. I get how that electric field is changing at that point.
Yeah. What you get is There we go. You get a vector, three-dimensional vector, which gives you the derivative, partial derivative in every direction. Which means that if you have
Yeah.
a field with just the magnitude, you take the del of that field and you get exactly what you described. The electric field at any given point is a vector, no? Yes, Gabriel, that is true because, as we established, it has to be true because otherwise you cannot take the cross. My question
Unholy
is,
tribal.
unholy thinkable.
Yes.
My question is, why does the electric field have a direction? Like, why is it R3? Why does it require?
Y direction.
Yes, exactly. That confuses me. Because as you get what I mean with the del, right?
I mean, I do get what you mean. Like, okay, like again, I've said that I don't know electromagnetism, but I'll restate just one more time. When we're discussing this, you shouldn't think of me as like knowing anything at all. Like, so we're essentially just on the same page. I'm trying to figure this out as well. But my headcanon is that physics notation is actually stupid. Okay? And the reason why it's like this is because there's actually so in my head there's actually two types of derivatives that are working in play here, right? um One type of derivative is just the usual take the gradient, find the slope of greatest ascent or descent type of derivative, which is what you're seeing when you write delta E, just as in delta E, right? And the other type of derivatives that are that are like at play here are like the ones that show up in the delta dot E and the delta cross E.
No, they are the same one. The difference is in that when you take a del to a function, to a map that's R3 to R, there we go. You can take it on a R3 to R, or you can take it on R3 to R3. And so in this scenario, you're effectively getting it of a scalar, which is why there's only one way you can slice that cake, because you. But when you're taking R3 to R3, then that changes things because all of a sudden your gradient itself.
It would be a tensor, yes, it would be the Hessian, the double derivative.
There we
I
go.
think.
Yeah.
Yeah.
The electric field is a set of all vectors that compose said field. It doesn't have its own direction per se, but an implicit direction encodes within it, in my opinion. Sorry, what do you
What?
mean by that? The electric field is a set of all vectors that compose said field per se, but an implicit direction encodes within it. I mean, yes, it is a set of all vectors that compose said field. What we are trying to figure out is why vectors.
Why does it have direction at a point?
Yes, we have already established that it's R3, and we know what R3 means. Our question is, why is it R3 and not R? Because R on its own would, like, intuitively to me, it makes a lot more sense. Because then, well, that's how I understand electricity. What does it mean for an electric field to have a direction? You have okay, so basically, Gabriel, you have a point in space, right? With this model of the electric field, a field with magnitude 1 at that point can point different directions. So we can either have it this way, for example, or we can have it this way. Depending on which direction it's facing, it would have different ramifications. I just realized I wrote down as blue and red, which makes it look like a compass, but we're talking about electric field here. So it has a direction. Now, the problem is that I just straight up don't understand why. Because if you place a particle near this field, then I suppose the answer would be in Hamilton. Now that I think about it, not Hamilton. My goodness, Maxwell's equations. That's because the curve.
Yeah, that's exactly what we're trying to figure out, Holy Spigot.
Why the electric field is modeled as a scalar field? Yes. And hi, the farm mate. Hi, it has been a long time no see.
Oh my god, Pharmaceutical Man 1404.
The pharmacy.
Long live the pharmacy.
How are you, mate? Busy. Busy. Really busy.
Might be wrong, but it has direction because electric field is the force per unit charges. Force is inherently directional. Yeah, that was my original answer. Is that the electric field would tell your test particle how to move?
So, but do you know why I don't like that, Ash?
Yeah, because of the delta E thing.
Well, a simpler way to put it is that then you need to think of your field as basically field of a force and not field of an interaction. Because in my head, the electric field is just energy, which doesn't have a direction.
Electric field is energy which doesn't have a direction. Let me think on this for a second.
Yeah, because in my head, it's just potential. What's happening right now? I'm just doing a bit of a relatively deep dive into Maxwell's equations, trying to learn some electricity.
Yes, I think I'm wrong on this one. The electric no, wait, hold on.
Can I give you, first of all, before we carry on, just a little nugget of advice?
Yes, do go on.
If you say that you're not knowledgeable about certain topic, I think you need to get better at not being knowledgeable about something. Because
I mean, yeah.
you're because you stated that you're not knowledgeable about this, and that is absolutely fine because neither am I. But you're picking a side and already saying like I think I'm wrong or that's what I was saying. If you're not knowledgeable, then don't develop an opinion. Just like try to figure out, try to get knowledgeable and then develop an opinion.
I don't. I mean, yes, I am switching sides, but I think that's a byproduct of thinking.
Don't have a side. Don't pick a side. Like don't go onto any side. Not yet. Way too soon.
Okay. Okay, then how do you think about this?
Well, the way I think about this, I have a question, and I'm just trying to get that question answered. I don't know Maxwell's equation, but I will develop an opinion nonetheless. No, because the thing with the force, that makes sense. The problem is that that would require a completely, if I'm not mistaken, that would require a completely different concept when it comes to an electric field and an electromagnetic field. And when I say completely different, I mean completely different. Like, the thing is, if you have that field, and if you say it's, force per unit charge, that makes sense, it's direction, right? Forces have a direction. But then it would sort of break down in different formalisms, wouldn't it? So, for example, that's one thing I remember. Lagrangian canonical momentum, right? Once again, what is the equation for the canonical momentum? I'm pretty sure I have it noted down here somewhere, actually. Do I? I'm not certain. Hold on.
I think you do.
I definitely have it on the other paper. Oh yeah, right, I do. Because it's this. This is canonical momentum. And like, I remember when Remco was teaching me about that, the reason why canonical, like an example they give me of why canonical momentum is more general is, one example is the fact that if you have a charged particle, then your momentum isn't mx dot anymore. Because it's mx dot plus q some kind of constant. So that shows that you clearly can describe, or at least like, this would imply that you can describe charge using the Lagrangian formalism, right?
Okay.
So you see the dissonance between describing the field as a force and using a Lagrangian formalism to describe it. You see what's confusing me?
Kind of. I'm still thinking, hold on.
because in my head, I'll just mention it to everyone else. In my head, if you have a formalism that depends on something like this, right, kinetic loss potential, then it would make most sense to just have the electric potential be the electric potential. So you just define the potential right here using the field, and then you just carry on. But that would require your field to be energy, and that would require it to be a magnitude, because you cannot have a directional potential. Even better, this would work, because if your field really would be R3 to R, then this would just be genuinely V, X, Y, Z. That is the R3 to R. But it isn't, which means I must be doing something wrong. I'm going to look into it again. Electric field.
You know, I think you lost me ever since you said that the electric field somehow has energy inside it. Ever
Not
since then,
has,
I
only
haven't-
is, because like in my head, in my head I'm thinking of electric field as just potential.
Electric field as its potential. Okay.
So imagine it this way, Ash. Yeah, you have some kind of particle in space, right? That particle
Yeah,
has
I
a
do.
particle has a position, right?
Yes.
So
yeah.
what you do is you take the position of that particle, you input it
Mhm.
into your V XYZ. That gives you back the potential energy of the particle. What
Okay,
I'm
give me a
saying,
second. Yes, okay.
yeah,
I got it. Move on.
and what I'm saying is that in my head the entire time, the way I was thinking about fields and electric field included, is that it affects the potential. That's what it does. Like it's inside the potential function right here. That's how it affects the particle. Which is why when the particle finds itself in like really high electric field, it just wants to get out of there because it has a shit ton of energy locked in the potential.
Ha, okay. I think I see your argument now.
But it's clearly wrong. That's the problem.
Okay. Yeah, oh yeah, okay. I see where you're coming from. Hold on.
It's even worse because, oh, this is confusing. On the website where they are like talking about the fields, they note down this equation: E is equal to fraction Q by 4 pi
Yeah.
epsilon naught R squared. You know what the problem with this equation is?
It's not even potential because I think you only have one R in potential.
The problem with this equation that this is the equation for a magnitude of electric field. Because hey, let's use the same character for magnitude of a field and a vector field.
Oh yes, this is why I like physicists, you know.
Equation
And I say that sarcastically.
to quote their website, equation 2 gives the magnitude of the electric field. This is magnitude of the electric field and uses the same. I'm not even mad at this point because I've been through too much physics to have
I
any
feel
feelings
like-
on this, but
Is it bolded or something? Like there should be some distinction. I don't know.
yeah, I mean, all of the vector fields are bolded. The problem is that you can't really see it because it's just LaTeX notation, and it's tricky to. I don't think it's bolded. I would assume it isn't, but like you have no reference point for what a bolded E and not bolded E looks like in that section.
Okay, I opened the website. I'm gonna read.
Yeah. Also, the website named PHP. Damn, they actually survived it just to make the website. This should be as weakly quantity as magnetic direction. For positive charges, the E field points away from the charge, and negative charges pulled towards the charge. So, okay, that makes sense. Okay, no, that makes sense. It's to denote the charge. Right. So basically, the magnitude is this, but charges tell you if it points towards or away. I like that. I do like that. So if you have a hypothetical particle that is the charged megaton,
Megaton.
m with a tiny q, the charged megaton, that's very different from a normal megaton, and then you have the anti-charged megaton, which it's unique because it's a particle that is identical to the charged megaton, only it has a flipped charge. It's wacky, don't think about it too much. Then if you swap their places, the field will be different. But crucially, the magnitude won't be. Magnitude will be exact same, the direction of the field will just be flipped.
Ah, okay. I see what you mean. But,
And no, that's not what I mean, that's just what it says. That's what it says on the website.
yeah, okay, well, I get the website's meaning. But the thing is, I guess, yeah, I mean, it is true, obviously, like, I can see it, but, like,
That makes sense.
that's
Then.
only true as long as you have only one charge in your system, no? Like, as soon as you add other charges, it's not going to be that trivial.
Well, I mean, no. This introduces the magnitude, right? This right here.
Uh-huh.
You can also, based on that, you have the magnitude. Actually, I think I see what you mean, because then the Q is like this. Yeah. I see what you mean.
Because it's gonna be that R squared term that messes everything over, because then you can't add linearly. So,
Well, okay, I mean, it messes things up, but it doesn't break them, does it?
I mean, I guess not.
I imagine it can't be too easy, can it?
Yeah.
That then makes sense, because then so we've gotten through that. Now let's think about the curl of the electric field. What does it mean for electric field to curl? Well, it means that if you have negative particles right here, positive particles right here, it would go in this direction. Oh, this is good. We'll go with this direction, which means that if we're doing... Oh, I know that on the other side, didn't I? Yes, this. Let's do y to z like this, and that will be our x. So, y to z... No, z to y, okay. Z... So we're doing z to y, and that's z to y minus y to z. So z to y tells you how much change in z increases this, which means actually we'd also need a... Also, I got these arrows flipped, doesn't matter. This makes... Oh, this is so close. I can feel physically the neurons connecting in my brain because... Yes! Okay. Think about it this way. You have particles in this kind of configuration, right?
Uh-huh.
What would be the arrows pointing? Well, the arrows all be pointing towards the plus, correct? I want to make sure. No, away from the plus. I did get them correct. Okay, so they will be pointing like this. But crucially, we only want to know them the sideways ones, which means that right here, the sideways ones would go really strong sideways, right here. But then the more we move to the right here, they would go no place sideways, right? Right here, they wouldn't go sideways at all. Well, they would go sideways slightly. And even better, as we move over, they would start going right, because they get pushed away by the plus. Obviously, there's more happening, and this exactly doesn't matter. The point is that there is a way for us to move forward that actually increases the magnetic field to the left, which means that if we then take a derivative of us going forward in relation to how much it's changing to the left, what does it tell us? It tells us the curl. Does that make sense?
I see what you mean.
Yes.
So you're moving in one direction and you're asking how much is the magnetic field changing in the other direction.
Exactly. And that gives us the curl of it. The only problem is that then we're subtracting it the other way. I need to make sense of that. So this right here is giving us this derivative. This right here then must be giving us this this derivative, like so. So we're moving forward, it's giving us the derivative to the left. So with the other one, we're moving to the left and it's giving us the derivative forward, and these two have to be subtracted from each other. So moving forward, it tells us how much it's curling to the left. If we move to the left, however, and that increases curl to the right, that means it's not actually curling, that means it's just increasing in magnitude. Yes.
Yeah, I think we are taking the magnitudes here, yes.
No. What I mean is that the reason why we subtract them off is because if both of these derivatives increase, that means we're not actually curling, we're just increasing the magnitude.
Ah, okay, fuck, I see what you mean. Yo, that's actually brilliant. Holy shit. Wow, okay. It all makes sense now.
Oh, I am so upset I don't have any more whiskey. Well, I mean, I do.
I have milk. I'm gonna drink milk to this.
Cheers to that. This was my can you hear the music moment. Oh my goodness, this was incredible.
Curl has never made more sense to me than now.
I would just like to mention it took me an hour, no preparation whatsoever.
Damn.
I am pleased. I am pleased with this, with what I've done here today. Because I actually understand Maxwell's equations now. It makes sense. Let's review. Actually, on this page, why not? So, we have 4 Maxwell's equations. What do they state? Well, now we understand the concepts. Let's see. We have del of D, which is rho v. Since it's a dot, this is basically the magnitude of change of the electric flux density. Great time to be board maker. Yeah, exactly. And the same one will go for the magnetic equivalent, and this is basically just divergence. Sorry, I keep saying magnitude. I should be saying divergence, right? Yes, divergence. Let me note down these two as well. I really want to make sense of this one with the magnetic in relation to time. So the curl of the electric field is equal to minus the magnetic in relation to time, which means if you want to see, because that means that if we have a high magnetic, that on its own won't matter. What matters is how much the magnetic is changing.
Yeah.
There we go. So this would cause our field to curl and then not.
Okay.
You increase the magnetic field, the electric field starts to curl inwards. It starts to curl towards the positive charges. Am I correct on that? Hold on, let me have a think. That wouldn't mean that you can just cancel out by increasing. That doesn't make sense. Crucially, this is also an R3, which means that's if this is our Z, this is our Y, then this would be our X. which means then the magnetic. So let's think about one dimension. X, Y, Z, because that's the notation we've been using, which means that this derivative right here tells us how much this derivative right here tells us if we move in the Z direction, how much the Y is changing. So it tells us how much it's curling to the left. High value means this effectively, these two arrows. That's what a high value means. Low value or negative value would mean them inverse, but crucially we're multiplying it by the basis of the x, which means we're multiplying it by the basis of right here. So that means that we're getting the curl in that direction, like this kind of curl. We're getting it based on this direction of the magnetic field. Oh my goodness, it makes sense. Yes, 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 yes. Oh, I need Wikipedia. I need a Wikipedia article about magnetism because I can just picture the GIF. Magnetic field. This basically, this. It makes sense. You apply a current, yeah, because the Maxwell's equation of because the Maxwell equation with the magnetic as well follows the same trend, which means that this is equal to partial D, partial T plus J. Apply an electric field in this direction, right? Right there. And what's going to happen is the magnetic field will begin to curl around it. That's basically what this states for electric and magnetic.
What is, wait, okay, hold on. Delta B by delta T. Okay, that one makes sense. It's just like how much charges are moving, right?
Yes.
And then what is the plus J here?
That's a good question. Let me see. J is the current density. And I would just like to mention the website's so brilliant. You can click on any part of these equations and it like explains what they specifically are. I just really like that you can also click on the plus and it explains addition. But J's current density, and that appears to be because total flow of charge per time over a cross section of area. So it's, oh, so that's just, yeah. Okay, so yeah, J is just I per A. Like this. That's because, so apparently if you have a lot of charge moving, so you don't need to have a high field if you have a lot of charge moving as well. Yeah. So the way you can think about it is, if I'm not mistaken, if you have, okay, so if you have in a certain volume, right,
Yeah.
1,000 electrons, right?
Okay.
Then this will affect the partial of the magnetic field in relation to time, right? If you then have like 1,001, then 1,002, 1,003, then you will get a positive partial derivative, right?
Yeah.
But if you have 1,000 electrons moving through a surface, right? And then all of a sudden you will have, so 1,000 electrons per second, and then you will have 2,000 electrons going twice as quickly, then you will have the same, magnitude of the field, because at any point there will be the same amount of electrons there. But there will be twice as many of them traveling through it. Do you get what I mean?
Okay, maybe, sort of.
Right, so like you have 1,000 electrons traveling.
Yeah.
So you have 1,000 electrons in a certain place. That causes a high magnetic field.
Okay, so just the electrons being there is already causing a magnetic field.
Well, yeah. That's because they have charge. They have the negative charge, so they will all, you know.
Aha.
So, okay. If you want, so basically, let's say you want the magnetic field to curl, right? You have two options. You can either have a container, a bucket of electrons, into which you need to keep adding electrons into the bucket.
Okay.
Or, second option, you need to have an electron beam that shoots out electrons.
Okay.
And you need to shoot out twice as many, twice as fast. So if you pause time, let's say that you have a beam which shoots them out at just the right speed, that it shoots out just one per n unit time, right? If you shoot out twice as many of them, twice the speed, if you pause the time again, you will once again have only one electron at a time. Does that make sense?
Wait, hold on. Wouldn't it be like twice the electrons at half the speed, or
No, it has to
Is
be
it-
twice the electrons at twice the speed, because whenever you pause for the same time, you only want one electron to be there. Because you want the field to stay constant. If you do it at half the speed, then all of a sudden, so you know, you have the amount of electrons per time that it took them to travel, if I'm not mistaken, and you want that to be
okay,
constant.
okay. I see what you mean.
Yes. So you shoot out 1,000 electrons in 1,000 seconds. At any second, you only have one electron.
Uh-huh.
You shoot out 2,000 electrons at 2,000 electrons. Wait, no, 1,000 electrons per 2,000 seconds. Well, you were gonna shoot out 2,000 electrons still in 1,000 seconds, but at twice the speed. Then still you're going to have only one electron at any point.
Yeah. That
So
makes
in
sense.
both of these scenarios, the electric field magnitude is always the same. Because you always have only one electron there.
Yeah.
But in the second scenario, where you're shooting them twice as fast, then the magnetic field is going to curl more. That's the J.
Ah. Okay. I think I get it.
This all makes so much sense. Oh my goodness. This all makes so much sense. Hour 22. Not bad. I'm gonna note it down in my drawing science notebook now. And I think I've gotten out of my system.
Gotten what out of your system?
The scientific itch to do some science.
Oh.
I was bored. No, that's why I started the stream. We might be doing these more often from now on, because I just like this one. So yeah.
Yeah. I could use more physics streams, honestly.
Yeah, exactly. So look out for streams with blue borders, because that means that was gonna be in science. So it's double-sided. Lots of fun stuff on the paper, exactly. But even better, lots of fun stuff that I understand now, which is nice. Anyway, I need to go get back to work, but this was certainly quite a lot of fun. So for now, that'll be it. Thank you everyone so much for watching and have a great day. Bye!